Hello everyone, my name is Pallavi Sharma and I'm currently pursuing PhD under the supervision of Dr. Manish Kansal at Thapar Institute of Engineering and Technology, Patiala, India. The title of today's presentation is An Efficient Numerical Approach to Approximate the Tensor Sine Function with the Einstein Product. This is the outline of the presentation. First of all, introduction, in which we will introduce some definitions related to tensors and some algebraic operations used for tensors. Then we will define what is a tensor sine function and then a novel iterative method to compute the tensor sine function. Then its application in solving Yang-Baxter like tensor equation, some numerical results to support our method, and then final conclusion. So, what are tensors? Tensors are basically generalizations of matrices. And what are matrices? Matrices are generalizations of vectors, and vectors are generalizations of scalars. So, at the very first moment, we start studying what are scalars, and then we move towards vectors, which are one dimensional array, and then from vectors, we go towards matrices, which are two dimensional array, and then if we study higher dimensional arrays, then we call them tensors. So just as matrix functions and matrix equations can be seen in modeling and computations where two-dimensional data is involved, similarly tensor functions and tensor equations can be found in multidimensional data. So research is ongoing to develop efficient algorithms for tensor computations, especially for solving tensor equations and defining tensor functions. So before we explore tensor functions and how to compute them, we need to understand some basic definitions and operations related to tensors. First operation, that is tensor multiplication. There are different types of tensor products. One such product is Einstein product, which generalizes the matrix multiplication to tensors. So if we consider two tensors A and B, here order of tensor A is n and B is nth order tensor, then Einstein product A star and B is defined as this equation number one. So this is nothing but the generalization of matrix multiplication. If we put n is equal to 1 and m is equal to 1, then we get the matrix multiplication formula. This product has been defined in this article, Solving Multilinear System by Tensor Inversion, which was published in 2013. Then here comes the transpose of the tensors. As we do transpose of matrices, similarly, we can compute the transpose of tensors just by swapping first 10 indices with the last 10 indices. So basically, we need even order tensor to compute the transpose. And similarly, trace of the tensor can be computed by summing up the diagonal elements, which are nothing but when first 10 indices match with last 10 indices. To analyze and compare tensors numerically, we also need inner product and norm of tensors. So for this, we define inner product of two tensors where both of these tensors are of order 2n. Then the inner product can be defined by this equation number 5. And from this inner product, we get the tensor norm as given in equation number 6, and we call it as tensor Frobenius norm. Now let's move towards tensor sine function. Before defining the tensor sine function, let's first recall what is scalar sine function, which is defined for all those complex numbers which do not lie on the imaginary axis, that is, their real part is not equal to 0, and sine of that complex number is defined as 1 for all complex number which lie in the right half plane and -1 which lie in the left half plane. Then in 1980, Roberts introduced metric sine function in this article, linear model reduction and solution of the algebraic Riccati equation by use of the sine function. He defined metric sine function for all matrices which have no eigenvalue on the imaginary axis by considering the Jordan canonical form of the matrix. Then he split the Jordan form into two parts. The first part contained the eigenvalues corresponding to the left half plane, and the second part was associated with the eigenvalues lying in right half plane respectively. Then sine of A can be defined by this equation number 8. Now let's generalize this definition to tensors using the Einstein product. Basically, At each place where matrix multiplication has been applied, we will use the Einstein product in case of tensors. So let here T to N, comma N represents the collection of all two nth order n-dimensional tensors. So basically we can only define the sign of tensors of even order. So if we consider such tensor A and its Jordan canonical form can be given by this equation number 9, then similarly, like just like as matrices, we split its Jordan blocks into two parts, one associated with left half plane and the other one associated with right half plane, then sign of A can be defined by this equation number 10. Here, diagonal tensor represents minus IP, comma IQ. These are two identity tensor blocks. Now, when it comes to the computation of tensor sign function, there are very few analytical methods present in the literature. Uh, so it becomes necessary to develop iterative methods for approximating such functions. So let's go through some existing iterative methods present in the literature. First method that we have studied is Corvaric method for finding metric sign, and this can be generalized to tensors as provided in this equation number 11. This other one is Newton's method, which can also be written in the tensor form as provided in this equation 12. And very recently, the authors Irfanifer and Hajarian developed a iterative method for computing tensor sign function, which have been provided in equation number 30. Now, these existing methods for computing the tensor sign function often face challenges such as low convergence rate, high computational cost, limited stability for certain classes of tensor. So our goal is clear that we will develop an efficient, numerically stable and rapidly converging iterative method for computing tensor sign function. So here we propose our method given in this equation number 14, which where the initial guess will be discussed later, and we denote this method by PM. Now to ensure the reliability and effectiveness of the proposed method, we now analyze its convergence behavior under some suitable assumptions. For this purpose, we have provided this theorem number 1, where we have considered a tensor of order 2n having no eigenvalue on the imaginary axis, and we consider the initial guess as alpha into a, where alpha is defined as 1 by norm of a square. Here norm of a is nothing but that Frobenius norm which we defined earlier. Then the tensor sequence generated from our proposed iterative method 14 converges to sine of a. In order to prove this theorem, we have considered the Jordan canonical form of the tensor A and then split the Jordan form into two parts, J minus and J plus. Then we consider the eigenvalues lying in left half plane and eigenvalues lying in right half plane corresponding to these Jordan blocks, and we apply sine of A by the definition. Then we applied this definition to compute the sign of this Jordan block J. And then we define a new sequence HK is equal to U inverse XKU, where initial guess is defined as H naught U inverse AU. Then using the proposed iteration, we compute this HK plus 1 using iterative method, and then we convert this iteration into scalars so that we can compute this limit which comes out to be 0. And from here it is clear that these scalar iterations converges to sine of those lambda, those eigenvalues, and hence our that new sequence HK converges to sine of J. But if these HKs are not diagonal, then we can do the same procedure for the eigenvalues of each iteration and we get the same limit again, and hence our proposed method, that is xk plus 1, or we can say xk, converges to sine of A. This finishes the proof. Now the next theorem presents the order of the method. that is 5. Our iterative method converges to sign of wave with the convergence order 5. And for proving this, we have considered this epsilon k as xk minus s, and then we have computed epsilon k plus 1. And when we applied norm on both sides, we get that norm of epsilon k plus 1 is always less than equal to this bounded part into epsilon k raised to power 5, and hence the order convergence order is 5. Now, the another most important factor in case of iterative methods is asymptotic stability. And for this, we have provided this theorem 3, which proves that our iterative method is also asymptotically stable. For proving this, we have considered the numerical perturbation generated at kth iteration, and then we compute numerical perturbation generated at k plus 1th iteration, which appears to be bounded, and hence the method is asymptotically stable. Now, after this, let's explore the important application of the tensor sine function using our proposed method. So, which is in solving this Yang-Baxter like tensor equation, which is nothing but generalization of Yang-Baxter like matrix equation. So, this is the nonlinear tensor equation 33, which is known as Yang-Baxter like tensor equation, and it has two trivial solutions, x is equal to 0 and x is equal to a. Now, in order to compute other solutions, we can use the sine function, and for this we have provided this theorem 4, in which we have considered the two solutions as a into I plus s by 2 and a into I minus s by 2 using the Einstein product. We can note that here I represent the identity tensor and s is nothing but sine of this tensor a. The proof can be seen easily just by substituting both the solutions in the Yang-Baxter like tensor equation, and both of these solutions satisfy the equation, and hence these are the solutions using the sine function. So we can just apply our iterative method to compute the sine of A, and then we can compute the solutions. So, in order to demonstrate the practical performance of the proposed method for computing the tensor sine function, we have performed some computational experiments to illustrate the advantages of our method over the others. And for this purpose, we have used some existing iterative method for the comparison, which are Corvaric method that we have defined earlier, Newton's method, and the very recent method, Ifanifor method. So we consider the stopping criterion given in this equation number 36, and all the experiments have been implemented in MATLAB 2020 2B version with the machine precision 10 raised to the minus 16. So let's consider the first experiment, in which we have taken a random tensor generated in MATLAB with the order 4, and we have defined its dimension as n and considered the different cases for the different values of n. So when we put n is equal to 5, then it becomes a random fourth order 5-dimensional tensor. So we can see for n is equal to 10, 15, and 20 also. In all the four cases, our proposed method converges in fewer iterations as compared to other three iterations. This is the purple line shows our proposed method, in which we can see even the error, relative error R, also appears lesser as compared to other methods. So hence we can say that our proposed method is superior than other methods. Uh, we have performed another experiment also, in which we have taken now sixth order tensor, and we have considered the dimension varying from 5 to 15. Fives, we have considered different values of n, and in each case our iterations are lesser as compared to other methods. In this experiment, we have also compared the CPU time, and which is also lesser as compared to other methods in our proposed method. So basically, from these experiments, we can say that our proposed method is superior than the other existing methods. So in final concluding remarks, we can say that our research investigated the sine function of tensors by generalizing the metric sine function, and we developed a numerical iterative method to compute this tensor sine function using the Einstein product. Then we performed the convergence analysis of the method and proved that the method has fifth order of convergence. And also we prove the asymptotic stability of our method. Then we explore the application of our method in solving the Yang-Baxter like tensor equation. And finally, we have performed some numerical experiments to enhance the superiority of our developed approach. So this is the references that we have cited in this article. Thank you.